Ladies and gentlemen, our event is about to start. Please silence your cell phones and take your seats. Thank you. Ladies and gentlemen, please welcome co-founder and CEO of NVIDIA, Jensen Huang.
Happy New Year, everybody. Welcome. We're going to talk about cars. We're going to talk about self-driving cars today. Last year, we introduced the Drive PX self-driving car computer, and I said three things. I said that in the future, when you build cars, it's going to be a lot more like a computer. That the ability for car companies and system OEMs to configure cars by connecting sensors and controllers one at a time and evolve it over time is going to be more and more difficult. That you have to approach it from a computing system perspective. Software is going to be a very big part of what you do, and ongoing improvements of the software is going to be very important. The second thing I said was that computer vision technology that had evolved up to this point using hand-coded features and engineers crafting pieces of code to detect objects in the world are going to be difficult to continue to advance to the point where we could have cars that drives itself. and that we would use a technology called deep learning. The third thing I said was that all of this computation capability is going to have to be done in real time. Because your car is driving through the streets, a lot of things are happening around the world, and you want to be able to detect it, understand what to do, and have the car keep you out of harm's way and navigate safely. So the third thing I said was we're going to need supercomputing technology. All of this we've been working on the last year, and today I'm going to give you an update on that. Several thousand man-years of effort have gone into advancing the state-of-the-art of self-driving cars at NVIDIA this last year. So first of all, I'm going to tell you the punchline. Ladies and gentlemen, the NVIDIA Drive PX2. This is the world's first in-car AI supercomputer, and it's designed to make it possible for us to realize the vision of self-driving cars. It has 12 CPU cores, 4 chips, each with Pascal GPUs in it, with a combined processing capability of 8 teraflops, with a special new set of instructions designed for deep learning that makes it possible for us to achieve 24 deep learning teraops per second. It's built with 16 nanometer FinFET. Altogether, this entire supercomputer fits in your trunk very nicely, the size of a lunchbox, 250 watts, all in that little tiny device. The computational capability of PX2 is equivalent to essentially 150 MacBook Pros. Imagine 150 MacBook Pros of processing capability in your trunk. All of this within the size of a school lunchbox, 250 watts. It needs to be water-cooled, and the reason why it needs to be water-cooled is because we want to be able to make it possible for you to have this operate in all kinds of severe conditions that a car could be enjoyed. Okay, so NVIDIA Drive PX2. But let me back up a little bit and tell you the reason why we're doing this. Our vision is to make it possible for us to finally realize the self-driving car. Now, there's a lot of ways you can think about the self-driving car. From a technology perspective, it's utterly amazing. If you ever enjoyed the process of having a car drive you to work, it's just a really wonderful experience. However, technology aside, the contributions to society is arguably incredible. Transportation, mobility is one of the most important things in society. It is central to how almost any culture in society is made. Humans are the least reliable part of the car. We represent almost all of the fatalities that are caused around the world, over 1 million deaths each year, and the human is the most unreliable part of it. So whether we're augmenting the human so that we could help people drive better, or replacing the human altogether, self-driving car technology is surely going to make a great contribution to society. Second thing, of course, if you can have cars that drive itself, all of a sudden it's possible for us to accelerate this entire movement of personal mobility as a service. Fewer cars on the road. The cars that are on the road are utilized more frequently. The convenience of having mobility as a service is incredible. And then third, fewer cars that are utilized more frequently will ultimately result in having fewer cars in urbans. And we'll be able to redesign our urban environment and make the neighborhoods more beautiful, more enjoyable. More parks will replace parking lots, and the convenient factor is incredible. And so whether you think about self-driving cars from the money that it's going to save, from the reductions in accidents, or the time that it's going to save us, or just the incredible freedom it's going to provide people who can't drive today for whatever reason, self-driving cars is going to revolutionize society. Our vision is to create the computing platform by which the entire automotive industry can realize this vision. There are 2 visions for self-driving cars today. One of them, this is a symbol that the Toyota team uses, which I really love. They call it the mobility teammate concept. In this particular model, the car is a virtual co-pilot A virtual co-pilot that arguably drives even better than you do. It drives better than you do because it's paying attention all the time. It's paying attention because it's a computer. It sees all around itself. And if we could create the technology to make it possible to drive by itself, this virtual co-pilot will keep you out of harm's way. I kind of imagine this idea where your car essentially has this virtual bubble around it, virtual force field around it. You never run into anything else around it. It knows exactly where to go, and it keeps you out of harm's way. The second vision is a car that has no drivers at all. In both of these examples, the computing capability necessary to achieve autonomy, self-driving capability, is going to be far greater than anything that's currently available. And we'll talk about that in a second and make it clear why that's so. In both of these visions, if we could realize it, the contribution we can make to society is really, really wonderful and great. And so our vision is to create the computing platform necessary to make this possible. The self-driving program loop basically works like this. There's a sensing part. You get all kinds of sensors. You want sensors that can see during daytime, during nighttime, during rain, during fog. All of the different types of conditions that you could possibly imagine surrounding the car, you would like to be able to sense. It could be radars, it could be LiDARs, it could be cameras, it could be ultrasonics. You have inertial measurement units, you have GPS. All of these sensors contribute to sensing where you are and what's around you. There are several different blocks that I'll talk about. The top block is the map, the precision map. That map was generated in advance. It was done through scanning, probably LiDAR scanning. You see these cars that are running around, mapping the world in 3D, measuring the world and precisely mapping every part. In the middle, that block is called localized. That has something to do with where you are. Based on what you measure, based on what you perceive, we have to figure out where you are within a few centimeters. The bottom block is perception. Perception, seeing everything around you, whether it's during daytime, driving directly into sunlight, in snow and fog and rain. Whenever it is, we need to perceive where you are and what's around you. And based on all of that information, we have to figure out a way to plan your path. So starting from where you are, you perceive the world. We figure out a way to calibrate that with a pre-known map. And then based on everything that's moving around you, your movement, where you are in the world, all the movement of all the other objects around you, whether it's pedestrians crossing or bicyclists or motorcyclists or cars that are moving all around you, you need to find a way to find your path. Okay, that's called path planning. You do this in basically an infinite loop. You just keep doing this continuously. You're perceiving the world continuously. You're comparing it against the map continuously. You're localizing continuously. And you're planning the next step continuously. And we do this as fast as we can so that we can control the car and make the car drive and path plan so that it keeps you out of harm's way. Well, it turns out all of this is relatively hard to do. Each and every single one of these blocks are hard to do. Perception is hard, localization is hard, path planning is hard, figuring out what sensors to use, using the right amount of sensors, but modestly so that we can make it cost effective, hard to do. All of these components are hard to do. And there's innovation, R&D, discovery, in every single component of it. Self-driving cars is hard. Well, it turns out that driving is hard. Now, when you think about highway driving, we've constrained the problem enough that highway driving has become relatively easy per se. I mean, to the point where grandparents can drive. We all largely stay in our lane. We're traveling about the same speed, and so relative to each other, we're hardly moving. Highway driving is relatively easy. And even then, there are many conditions by which highway driving hasn't been solved. We have highway driving in all kinds of conditions. If a truck carrying some junk, some parts of it fell off onto a road, that happens, as you know, pretty much all the time. And when that happens, your car has to do the right thing, take evasive action, and keep you out of harm's way. So even highway driving is hard. But we can't realize the full potential of our vision unless we can solve also city driving. Now, in city driving, almost none of us are going in the same direction. You've got cars coming sideways, you've got people walking all over the place. Bikers are, of course, in the same road that you are, motorcyclists. And people are, of course, sometimes following the rules and largely not. And so you can't read a manual from the DMV and figure out exactly what program to write into your car to cause it to drive properly. And so city driving is very chaotic, it's very, very hard, and the perception problem, as you can imagine, explodes. You have to perceive all kinds of cars, all different types of people, all different types of bicyclists, all different types of environments. Sometimes the road is being fixed, sometimes there's construction going on. Sometimes the lane is painted over from a new lane, and all of a sudden the number of lanes that you look at with your car is rather confusing for the car. And so everything around that environment is chaotic. It's complex, it's unpredictable, and oftentimes it's even hazardous. So self-driving cars are hard. The biggest problem at the core of it is perception. The biggest problem is perception. First of all, what is happening around me? What are things that I should be concerned about? And how should the car deal with it? The perception problem is at the core a very difficult problem. Well, as it turns out, the moment of Shazam, the Shazam moment, came several years ago. Computer scientists have been trying to figure this problem out for a long time, and several simultaneous innovations happened in the early part of this decade that made it possible for us to imagine solving this problem for the very first time. Work that was done by Geoff Hinton at the University of Toronto, Yann LeCun, Andrew Ng at Stanford, Yann was at the New York University. Work that they were doing independently on artificial intelligence networks came together to solve this problem in a really, really huge way. Yann LeCun's convolutional neural net, which makes it possible for programs to detect important features by itself if you gave it enough images, if you gave it enough data, if you gave it enough examples. Geoff Hinton's work on backpropagation and stochastic gradient descent makes it possible for us to train and essentially, through a large amount of examples, program this network by itself, to the point where no engineers, no computer vision engineers need to program this network at all. That breakthrough is called deep neural nets. That breakthrough was made possible in the early part of this decade, just several years ago. However, it took an enormous amount of time to train the networks. These networks required trillions and trillions of operations to train. And the training of those networks, just to put it in perspective, took months and months and months. Now, to train a network for several months on a particular data set is largely impractical. Nobody would possibly imagine doing it. Because you need to iterate on it, you need to see if that network was going to do what you think it's going to do. And so the training time took too long. Simultaneously, in those three labs, Andrew Ng's lab, Geoff Hinton's lab, Yann LeCun's lab, and the folks at NVIDIA Research, headed up by Bill Dally, worked together to make it possible to take advantage of the CUDA GPU that we invented to accelerate these neural network training. We were able to accelerate the training by 30 to 40 times. What otherwise would have taken a year to train a network now took a month, or excuse me, took a day, took a week. And so what took a month now took a day. And so it is now possible for us to train these incredibly complex networks on very, very large data sets to recognize objects of all kinds. Deep neural net, deep learning, is a groundbreaking piece of work in computer science, and most people compare it as large of a contribution, a large of a breakthrough as internet or mobile computing. All of a sudden, the race is on. The unimaginable actually happened in the year 2012. Alex Krizhevsky, over at University of Toronto, created this network called AlexNet, and he submitted it for the competition of ImageNet. ImageNet is 1.2 million images that you use to train whatever it is approach that you use, and you're tested on about 100,000 of those images. What was amazing was Alex's network, AlexNet, He never programmed a single line of code necessary to detect specific objects, won the competition of ImageNet in 2012, and beat computer vision architects, computer vision feature detectors, computer vision algorithms that took the last 20 years to create. AlexNet got the attention of literally everybody in visual computing, everybody who was doing this work. Subsequently, over the last couple, 2-3 years, more and more submissions happen. And if you look at the blue dots are hand-coded features of computer vision. 2012, you see those two green dots based on deep learning. Since then, almost all of the submissions have been based on deep learning. Handcrafted computer vision approaches no longer can compete. And started this year, later this year, Microsoft and Google announced that their deep neural nets beat the best human recognition in the world. So now, deep neural nets has achieved superhuman image recognition capability. This is an enormous milestone. Baidu, just recently, headed up by Andrew Ng's lab in Silicon Valley, announced that DeepSpeech 2 was able to beat humans in language recognition. Microsoft worked with China University of Science and Technology, and their deep neural net beat a college student in an IQ test. And so now, we recognize that deep learning is able to achieve superhuman perception capability. Now the question is, how do we harness all of this capability and put it to work in helping to solve the self-driving car problem? Our strategy has 3 prongs. The first prong of our strategy is to ensure that to work with the entire ecosystem of deep learning and artificial intelligence to make our GPUs able to accelerate the work that is done all over the world around deep learning and AI. Today, these are the frameworks that are offered around the world. Every single one of them are accelerated by CUDA GPUs. By using NVIDIA's GPUs, we can accelerate the training process of deep learning by some 20, 30, 40 times. What otherwise would have taken months to train now can be done in days, and we can therefore create faster networks, better networks, more robust networks, and use it for more things. The number of applications that we're seeing around the world as a result of this movement is really quite utterly staggering. If you haven't had a chance to learn about deep learning, just simply type in deep learning or type in modern AI or some search, and you'll discover incredible amounts of work being done in this field. So our first strategy is to develop and work with the entire ecosystem to accelerate every single framework of AI in the world. From Facebook's Big Sur, Google's TensorFlow, IBM Watson, Microsoft CNTK, all of these frameworks are now GPU accelerated. If you're doing deep learning work, if you're doing AI work, and you have a PC or workstation or a server with NVIDIA GPUs in it, your deep learning training will be accelerated to a level that is almost incomprehensible. To be able to accelerate a particular application by 20, 30, 40 times is a very big impact. Whether it's education or startups, NVIDIA GPUs are now used by deep learning frameworks all over the world. Okay, so if you're doing work in this area, whether you're training your network on a PC or in the cloud, you could access NVIDIA accelerated GPU frameworks all over the place. The second element of our strategy is to create the computing platforms so that anybody who wants to enjoy deep learning and the work that they do can enjoy, whether it's in the cloud, in a PC, in a robotics platform. The robotics platform is called Jetson. Jetson is binary compatible with NVIDIA Tesla, which is for your supercomputer in your cloud, which is binary compatible with NVIDIA's Titan X, which is used in your PCs, and it's also binary compatible with the work that we're doing for cars, NVIDIA Drive PX. One single architecture, one singular platform, deep learning everywhere. And here's the last part. The third part of our strategy is to enable the ecosystem, enable the world to enjoy deep learning and the work that they do by creating an end-to-end platform for deep learning. From the moment that you start training your networks, to develop that neural net, to deploying that neural net inside a car, we're going to solve this problem from end to end. I want to show you that today. We're going to solve this problem from end to end. Deep learning platform for training, it's called the NVIDIA Digits, to a deep learning network, to the in-car AI supercomputer so that you can quickly deploy it into your car. The way we see this loop ultimately for cars is it's going to be difficult, nearly impossible, to guarantee that your car has seen every possible scenario on the day that the car goes off the lot. We see that this new world will be a cloud-connected Internet of cars, Internet of Things architecture, where your car goes out the lot super smart, ideally nearly superhuman, and yet as it encounters new conditions that it doesn't understand, or if it performs a task that is different than you otherwise would have done, it would report it back to the cloud. We would very quickly train the network and re-release the new network to the world. All of a sudden, because of the experience of one car, every car on your network became smarter. One of the reasons why we believe in this is that ultimately we believe that the car companies have to own their own network, their own deep neural net. Every car company, because the deep neural net is such an essential part of your driving experience, ultimately this body of work has to be owned by the car companies. So our strategy is to create the platform by which these networks could be created and maintained and improved and refined over time. Okay, so our last strategy. Strategy number one, to ensure that NVIDIA GPUs accelerate every single possible framework for artificial intelligence development in the world. So irrespective of what framework you believe you like to use, number one, it will be GPU accelerated, it will be CUDA accelerated. Number two, that we would have platforms that you can deploy into, whether it's in the cloud or the PC or the car or robots, whether it's drones or machines. And then third, for the car, for all these platforms, to develop an end-to-end development system so that you could train the network, refine the network, deploy the network, and continuously enhance it. 3 parts of our strategy. Now, we've used this platform ourselves over the last several months to develop a reference platform. We call it the NVIDIA DriveNet. Now, we imagine that car companies all over the world will develop their own network, and I'll show you some examples of that in just a moment. However, in order to test out this end-to-end system, we're testing our own self-driving cars, creating our own neural net, and the part that is really amazing is this. Look at the progress. We've created a network, it's called the NV DriveNet. It has 7 inception layers. Basically, it's 9 inception layers. It's basically 9 deep neural nets nested within itself. A very, very, very deep network. 37 million neurons. And by bombarding it with an enormous amount of data and examples, we're training this network to be able to perceive the things in the world. It takes about 40 billion operations to run it through the network one time. It's able to classify or recognize single objects, multiple objects, and it could even classify every single pixel to tell you which pixel this pixel belongs to, which object this pixel belongs to. Now, if you take a look at the rate at which we've been accelerating, this is one of the most important parts of doing deep learning and neural net training. The velocity by which you're improving is arguably the single most important thing. And the reason for that is because you're going to be iterating over time. Over just a few months, our internal team of experts have been able to achieve nearly world-class levels. The #1 Kitty score, this is a benchmark and a data set that's used for self-driving cars. The #1 score is posted by Andrew Ng's team at Baidu. We are very, very close to the #1 score. However, the big difference is this. Ours run in real time. And so this network, because we want to be able to put it into a car, has to have the ability to actually recognize things in real time. And so the NVIDIA DriveNet, in just a few months, look at its progress and imagine where we're going to go. And so just to show it to you, let's now see what it can do. Let me introduce Mike Houston. Everybody give him a round of applause. Mike heads up the development of our neural net. And Mike, what are you going to show us today?
So why don't we start with the Kitty data sets. This was developed with Karlsruhe and Toyota. And so it's one of the standard data sets that's used to test the ability for things to detect objects. There's also a few other parts of the data set for things like object tracking, depth estimation. So we took NV DriveNet and we trained it to excel at doing car detection. So here's the raw output. There's no tracking, no other computer vision techniques. This is raw detection per frame. So you can actually see how stable the detections are. And with a few extra steps, this can be turned into a production network with things like tracking. So the training set that we used has 7,400 images, and there's 33,000 unique objects, unique cars that we're given to train with. So how this works is that 7,000 images isn't enough to really train a very deep network. So we take many, many rounds through the data, and we add forms of randomization to the data. So we'll do things like crop and warp and stretch and manipulate color space to help make a more robust network. We can train this network actually overnight with the data set provided, and this is the result that you get. So as Jensen said, it's been a few short months. Thankfully, we actually had two teams competing against each other internally on the network using slightly different techniques, and this is the result that we get. But we can take it a step further. So the neat thing about how neural networks work—
Now, before you go any further, Mike, so the first thing is you train the network, and it takes about a day. And if it had no GPUs inside, it wasn't GPU accelerated, it would take about a month. But the initial data set you trained with, the network that you started with surely wasn't trained to this level of capability with just a few thousand frames and a few thousand images.
Right, so we start actually by training a very large data set. So we actually start with the ImageNet data set, and it trains a very, very robust feature descriptor, much better than you can get by hand.
So this is 1.2 million images that we trained the network with.
Correct.
And it's trained to recognize about 1,000 different classes, different things.
That's right.
Right, so
we take those actually 1.2 million objects, but it's actually not enough to get the feature descriptor hardened enough. So we actually manipulate that to make it look like 120 million objects to train with.
So you trained this network with 120 million objects, and it took about a month to train on a GPU-accelerated server.
That's correct.
Mm-hmm.
Okay. And so
now, just pause there for a second. It took a month to train the original network with the ImageNet data set. Without GPU acceleration, that month would have been a couple of years. Reducing it down to a month so that we can practically train the original data set, the original neurons and weights and the parameters, so that it could be now used for this new set of data, so that it could be trained to enhance for this type of application. We had to start with a pretty robust network to start.
Yes, I mean, so the basis of our network was actually one of the winners from last year, one of the Inception networks. And I mean, this dominates the rest of the old computer vision approaches. So that's where we start with. But because we built such a robust feature descriptor, we can now retarget it for other similar applications. So instead of doing classification, we can use that same feature descriptor and now teach it to do detection very robustly. And there's just minor modifications for the network. But now what's cool is once we've done something like this, which is a single class-based detection, we can now do something much harder that actually isn't more computationally expensive because we already did all the work, all the initial learning in the network. And so we can retarget to a multi-class data set. So this is an upcoming data set that will be publicly available soon. It's the Cityscape data set. It was developed with Daimler. So there's more training images, and they're very, very finely segmented and detailed. It's a very modern data set. So we took that same network that we used for the Kitty data set and pulled in this data and retrained. And because we can retrain so fast, we're able to iterate very quickly to end up tweaking sort of the algorithms and how we set up the neural network and exactly how we train to get these types of results. So we trained for 5 different classes here. So pedestrians, street lights.
So not one engineer coded something to detect a man walking across the street in a suit.
That's right. It's
2 ladies walking down the street. Not one feature detector was coded by hand.
Correct. It's basically like holding up millions and millions of flashcards to the computer and telling it to learn, and basically nudging it in the right direction when it gets things wrong. So besides even the classes, we also had to train the tightness of the bounding box as well. So this is all work in progress, and it was done very, very quickly. But as you said, because we're not having 300 engineers sit there and hand code features, we can turn around and experiment so fast. Basically, you're now using compute time, which is relatively cheap compared to engineering time in order to do these experiments. So we can turn things around very fast. So the Cityscape data set is actually initially designed as a segmentation data set. So imagine basically hand coloring in all the people or all the cars and things in the data set. So again, we took what we trained here and we turned it over into a segmentation network, as Jensen said, where we do per pixel labeling. So we can switch and show you the results of that. So this was done with only a few days of research and training, but it shows that how quickly you can turn things around.
So in this particular case, not only are you detecting a car, you're detecting all of the pixels that are associated with the car.
Right. So where this gets important is if you think about needing to calculate free space in the scene. So it's sort of like if you ask a child to take a crayon and say, color the road. Color things I can drive on. Okay, color the people, color the cars. And so this gives you the next level of perception, saying, well, what can I drive on? What is this thing at this pixel that I'm looking at? So it's a much more robust way to handle perception in a car. In a practical solution, you're going to combine all these techniques.
And this is still the same core network. We taught it to recognize one thing, and then we taught it to recognize more than one thing, and then now we're teaching it to recognize which pixel associates with what thing.
That's right. So once you can train a robust enough initial feature descriptor, then everything becomes a fine-tuning exercise. So anything that's visual, we can retarget very quickly into detection, segmentation, multi-class, a bunch of other things. Now, to really show the power of this, though, so these were more of our research exercises on sort of research data sets. But we had an OEM, Audi, who was nice enough to actually give us a really challenging data set. They wanted to see, could we really make neural networks work in very difficult situations? Because this is one of the things where if you are an engineer and you're trying to hand-tune those features, it's just brutal to deal with really difficult visual conditions. So if we look at the data set that Audi gave us, so we trained, they gave us 27,000 frames and 120,000 instances of vehicles to train on. And so we picked one of the more challenging data sets. This is in snow with road spray coming off the road. Again, there's no tracking or any sort of any gains here. It's just raw detection every frame. And it was actually the point where there's that third car there where we actually thought we had a bug in the network because as humans, we struggled to see it until we closed much further down the scene. And the idea of trying to hand code features or even use very shallow machine learning to be able to capture some of the difficulty here is just daunting. It takes a lot of time. But again, we're able to take the data from one of our partners, take our network, and retarget it overnight to get to this quality. Okay? So there's still more work to go and higher resolution and more speed, which is why we need all the horsepower that we're about to put in PX2, so that we can run more cameras, higher speed, and even deeper and fancier networks to get better and better at our ability to detect difficult scenes.
That's really amazing. Thank you very much. Good job, Mike. So that network called DriveNet is running on currently a Titan X. And if somebody can later bring me a Titan X so I can hold up what a Titan X looks like. A Titan X is basically NVIDIA's highest performance GPU that's used in desktop PCs. Running on a Titan X, just now the NV DriveNet can achieve about 50 frames per second. Now, Mike said that basically it's brute force at the moment, and there's going to be plenty of tuning. On the other hand, we're going to keep making the network more and more robust and arguably more and more deep, and then be more and more processing. And so the point is that it takes something like this, like one of the world's highest performance GPUs, to be able to do deep learning at the rates that we're talking about. Now, at the moment, we think that the right answer is to throw a lot of computational horsepower at the problem. And the reason for that is because we're looking for we're doing R&D at the moment. We're trying to develop a great network. We're trying to discover what deep learning can do, the outer fringes of the possibilities of it, the last thing we want to do is to struggle with the computing resources inside the computer. So we put to task deep learning on a Titan X. I'm going to come back to that in a second because almost everything I'm going to compare to later to give you a sense of what a PX2 is going to be compared to a Titan X. Okay, so this runs, NV DriveNet currently runs on, thank you very much, thanks Paul, runs on a Titan X at 50 frames per second. And so this platform is used internally for us to develop our reference neural net, reference self-driving network, perception network, we call it NV DriveNet. But there's amazing engineers all over the world that are working on the NVIDIA platform. At Audi, Audi is using our NVIDIA GPUs and our NVIDIA platform called Digits and PX for them to do their work around self-learning. This is really an amazing achievement. In just a few hours, the Audi engineers were able to use the NVIDIA platform to train a network that can recognize signs, the German road signs, at a level that beats every hand-coded computer vision approach. In fact, if you look at this, this is the German road signs test, and the #1 score is by the Swiss AI Institute, and Jürgen and his researchers achieved the #1 score on that thing with a deep neural network. What's really amazing is this: the #2 score is human. So the deep neural network is now able to achieve better perception recognition capabilities of road signs than a human can, and completely beat hand-coded computer vision approaches. The folks at Daimler Mercedes are using the NVIDIA platform for their deep learning work for self-driving cars. And you can see here what they've been able to achieve with deep learning is really quite remarkable. Notice their pixel labeling and the pixel segmentation. It's almost perfect. What every single pixel that's associated with the car, every single pixel is associated with the person, the bicycle, the tree, the building, the road, the sidewalk, done incredibly well. And so this network has been able to essentially pick out what every single pixel is associated with. The folks at ZMP, they're a famous Japanese company who's building a robot taxi that's going to be deployed by the Olympics in 2020. They're using NVIDIA platform for deep learning as well. The folks at BMW are using it not just for self-driving cars, but also for visual quality inspection on their manufacturing lines. Preferred Networks, another Japanese company working on artificial intelligence at a cloud, large global network scale. Their vision is to apply deep learning with all kinds of Internet of Things connected to it, whether it's robots or machines or drones or cars, and to apply deep learning to collect data and make all of these devices and services smarter. Preferred Network is a partner of Panasonic for smart cameras, Fnac for smart robots in manufacturing, and also Toyota. Ford is using our technology for deep learning as well, and they've been able to achieve really quite remarkable results in a very short period of time. But there's so much more to do. There's so much more to do. Not only do we want to be able to recognize objects, we want to be able to recognize circumstances. There are many circumstances that we drive to on a daily basis that we take for granted. There are many roads that we take where there are no road lanes. There are many roads where it's not even clear where the lanes are. And if you take a look at the lanes on that snowy road, it's kind of hard to tell exactly where the lanes are and where you should keep. Should you follow the lanes or should you follow the cars? There are all kinds of conditions by which surprising circumstances happen. This example of the bicyclist that comes sideways on the car. Every bus is not the same. There are passenger buses, public transit buses, where it's okay to just drive by. School buses, you should stop. Every truck is not a truck. Some trucks are ambulances, and you should pull aside. All of these different scenarios, not only do you have to recognize what they are, but understand the circumstances, the special circumstances. These are all trainable things. So whereas today we're focused on training detection, perception, very shortly we're going to move towards training for recognizing circumstances. So that's the first part. The first part is the platform by which we can train our networks to create that deep neural net that we will ultimately run on Drive PX2. Now, before I show you the next part, Drive PX2 is a computer, it's a supercomputer, and has an enormous amount of processing capability. But one of the great challenges of a self-driving car, with all of these streaming sensor information and the vast amount of processing that we have to do, it is the ultimate system software challenge. This is the union of real-time computer graphics challenges and supercomputing work coming together in one. The amount of system software that we've been able to leverage as a result of our 2 decades of work around real-time computer graphics and all of the work that we've done here on deep learning coming together in a body of work we call DriveWorks. DriveWorks, the operating system, the algorithms, the middleware, the streaming pipelines, all of that comes together, has to run on this incredible processor, incredible computing platform called Drive PX2. Lots of system software, lots of algorithms, lots of engineers work on this. Several thousand man-years of work have come together to make DriveWorks possible. Okay, so now we're going to show you what DriveWorks can do. Miguel, now Miguel is he's not going to be on stage. Miguel is going to be in the back, but I promise you Miguel is actually in the back controlling this. Miguel, are you back there?
I'm here. Can you guys see me? Good. All right, so let me show you a sneak peek of what we're working on for DriveWorks. Before we start showing some of the results we're obtaining, let me describe to you what is the current sensor platform that we're using. We're using basically a standard car that is being equipped with cameras. We're using 6 cameras in this case, 4 surround view cameras, front, left, rear, and right. And then we also add an additional 2 cameras, which are a narrow field view on the front, a narrow field view on the back. Now, these are standard automotive grade cameras. They're 1 megapixel RGB cameras. And in addition to these sensors, we're also adding LiDARs. We have 4 LiDARs built into the car. We have 2 of them are focusing on the front and the rear bumpers, looking forward and backwards for collision detection. And then we have 2 more on the roof with a certain pitch angle to be able to do reconstruction and getting 3D height and the structures out of the space around the car. In addition to these sensors, we also use a standard GPS, standard quality GPS, which provides you an accuracy of about 2 to 3 meters on positioning. And then we also look at the car sensors, such as speed of the wheels and turning angle of the front wheels and such. Now, what I'm going to show you is...
Now, Miguel, before you go, so we're using these 4 LiDARs. They're Quanergy LiDARs, right? They're 40,000 samples per scan, and we're scanning them 10 times a second. So 4 LiDARs, that represents about 1.6 million samples. We have 6 cameras, each 1 megapixel, as you've already said, and we're of course updating those at 30 frames a second. Now, we chose this configuration of sensors. We chose this configuration of sensors so that we could test out the entire platform for self-driving cars. Now, there's a lot of different configurations you could imagine. You could imagine, sweeping singular LiDAR systems. You've probably even heard there are different LiDAR systems that could be maybe 4 different LiDARs that are oriented in different angles, so that it could remove self-shadowing and deal with higher resolution images like that. And so there's a lot of different ways you could put multiple cameras in the front, some with long distance cameras, some wide angle. You could use stereo cameras. We could make all of those choices. We decided not to, just to keep one particular configuration, but our partners are going to want to use configurations of every single permutation I described. And so one of the most important things is to develop a platform by which any car company could decide what is their configuration of choice. All of those sensor information would come into that sense block that I told you guys in the beginning. We would fuse it, and then we will process it from that point forward. Okay, you could train your network by the fused information of all these different sensors, however you desire. Okay, Miguel, go ahead. Sorry about that.
Sure, no problem. So what I'm going to show you is, to be able to show some results here, we recorded the sensor output to disk, and then what I'm going to do is I'm going to be replaying the sensor, but I'm going to be running all the algorithms live in a computer. So here you can see what the data looks like. This is a recording taken in up in Santa Clara. This is a 101 freeway drive. And you know.
Now, just remember for the audience, Miguel's currently not driving. He's actually in the back, sitting next to a workstation, and so the video is streaming into the computer. However, the processing of this video is all being done in real time. Okay, so the processing is all being done in real time. The video has all been pre-recorded, streaming in. Okay, go ahead.
That's correct. So now you can see here the video. Let me show you also the LiDAR data. So this is 4 LiDARs. And what you see here is the accumulation of all the measurements that the LiDARs are taking. We can turn some of them off. So you can see this front LiDAR, the front roof LiDAR, the rear roof LiDAR, and the rear bumper LiDAR. Right, so...
and we recorded all of this in our driving experience down 101, right, in Santa Clara.
That is correct. Yes. All right, so now what I'm going to show you is the different stages of the pipeline where we take all this information and do something useful with it. The first thing we need to do in the perception pipeline is try to figure out where the car is so we can relate all the sensors together and we can fuse all the sensor information. So to do that, the first thing we do is try to estimate car motion. And we do that by running a structure for motion pipeline. And let me pause the images. So basically what we're doing is with the 4 fisheye cameras, we are detecting all the features, all the points in those images, for all the different views. In this case, up to 8,000 per image. And then what we're doing is, as the car is moving, we're trying to correlate which points are which in all the sequences of images, so we can do a reconstruction.
So you're tracking let's say 8,000 points. You're tracking 8,000 points per camera, so 36,000 points, and you're tracking these 36,000 points in free space, in 3D space, through 30 frames per second. Is that right?
That is correct.
Okay.
So with all these points, what we do is we run, as I said, a structure for motion algorithm that is allowing us to place those points in 3D space. So we're converting them from 2D to 3D based on how things are.
Now remember, the car only saw camera information, and the camera information is just a bunch of numbers that is coming in through 4 cameras that's surrounding this car. What Miguel and his algorithm has done is through the motion that we're going through space, calculate the 3D environment around it, structure from motion. Okay.
That is correct. And additionally, by computing that structure from motion, we also are able to detect the motion of the car, and we can determine how the car has been moving through, while taking those images. So we can see here, this is the path that the car has been taking as we've been capturing all the video and processing it. Right. So once we have this motion, once we know how the car is moving, then we can bring in the LiDAR information. The LiDAR data is relative to the car, right? It's just distances of any points where the LiDAR beams hit as the car moves through space. So to combine all that together, we need to know how the car is moving, which we obtain through structure for motion. Now we can put all that together then into what is called an occupancy map. Basically, it's a probabilistic map that tells you, in the space around the car, which areas of that space are occupied by objects and which areas are not.
Miguel said occupancy map in Spanish.
Yes.
Go ahead, Miguel.
Exactly. So what you see here in the image is, the whiter the points are, the more probable there's an obstacle. The darker the points are, the less probable they are. And as we travel through, we can see, these are moving obstacles that they're giving us really bright points, and then they fade out as they move away. And we have on top, obviously, structure for motion that gives you some in relation to the motion.
Okay, so now our car knows how we're moving through space, and it could detect that there are objects around us.
That is correct.
Okay.
Exactly. So the next step on the perception pipeline is try to understand what those objects are. So for that, we do two things. We are running, as I mentioned earlier, we have two narrow field of view cameras, one in the front, one in the back. We are running DriveNet on those cameras. We are just taking those images in and running them through a neural network that's been trained to recognize cars, different classes of cars, SUVs, buses, and such. And we are running that as in parallel with the rest of the algorithms. Now, the second part of the object detection we do is we look at that occupancy map that we were discussing earlier. We detect the moving objects in the map, and then with those, because the grid that we have here is in world coordinates, we can then establish positions of objects. Let me pause it. Is positions of objects, relative speed to our car, and because we have the neural network that tells us what those objects are, then we can also put a class to them and then understand what those things are as they move by us. Okay, so at this point we are.
So now I have a model of the world around me now.
Correct.
Okay, I know that I'm traveling through space and I have a model of the world around me. Now what's next?
The next step is to figure out where we are in a map, localize ourselves within the lanes that we're driving, so we can actually then run more algorithms to do path planning and motion planning and navigation. So the localization is what we're doing here. We are taking a high-definition map. This is the high-definition map from here that has been computed offline by driving with cars with complex sensors like LiDARs, differential GPSs, and such. So it's a very accurate map. And then we're taking our GPS signals, which are these marked by these icons here, and we also know how we're moving based on our structure for motion algorithms. And then what we're trying to do is place out the car in the right lane, at the right distances as we're traveling, and compensate for the errors of the GPS and the errors of the measurements at the same time. And this is what we're seeing here. I mean, we can see, for example, that the GPS does have an error because it's placing the car on the side, and now it's doing some.
And so the point that you're trying to make is that GPS just simply is not good enough.
That is correct.
Right? GPS is accurate within several meters, but we need accuracy within several centimeters.
Exactly, that's correct. Now, in addition to just this, the localization, we are also running a simplified path planner that allows us to figure out, the current lane, whether it's viable to be driven in, or whether we need to switch lanes and what sort of trajectory the car should follow to do that. As we can see here, the path planner is just giving us the current lane in green because that is drivable, and then alternate lane changes. Now, as other cars are driving by us, we can see that we're trying to estimate that path, and we see that there's an obstacle, so there's a bunch of paths that are not valid until we find the one that is valid, that will allow us to change lanes without colliding.
That's really terrific. Okay.
So, and then putting everything together here, this is the additional LiDAR, the 3D reconstruction of the world with the LiDAR data.
And so, Miguel, what we have here is that we've taken all of the sensors that we have, we've fused them, and we figured out where we are in space, how we're traveling through space. We registered that with a map, a high-definition map, and as a result of that, we know what's the world around ourselves, we know where we are, and from that information, we can plan a path that is comfortable, that is safe, that takes into consideration the kinematics of the car. Lots of computation that needs to be done on the path planning side, and as a result, your car is driving nicely down the highway. Okay, thank you very much, Miguel. Good job.
Thank you.
Okay, so as you could see, with the sensors, with a powerful enough computer, and Miguel is also running on a Titan X, with a powerful enough computer, and all of these deep learning algorithms, sensor fusion algorithms, localization algorithms, path planning algorithms, all of this working on one software stack on one computer, it is possible to imagine yourself navigating down the road, down the highway really safely. Now, of course, this isn't the information that the driver sees. One of the most important parts of self-driving cars is for you to gain the confidence that the car sees everything around the world properly, that the path that it plans to take is consistent with the path that you think it ought to take, and then over time you develop confidence in the self-driving car capability. And to show you that, the integration of all of this into the user experience, where Drive PX now sends information, all of this information, to Drive CX, our infotainment system, so that it could be displayed all in real time so that you can gain the confidence necessary to self-drive. To do that, we have Justin, who's going to come up and tell you all about that.
Hey,
Justin?
Hey. So I want to show you what we're working on to bring all of this in here.
All right.
It's enormous, but
well, you know,
yeah.
I think that you now have the world record for the world's largest infotainment system.
I think so.
Yeah.
So. Yeah, and like you said, I think any self-driving experience needs to be considered from the cockpit, from the user experience standpoint, because that confidence, when you get inside of a vehicle, you can't see the body language. You don't know what the car's going to do. So we need to bring and distill all of this incredible amount of information into the car itself. So like you were saying, there's millions of points per second coming in. We can't just throw all of this at the driver as they're going down the road. They won't understand what's happening. So we need to distill and refine the localization of where the vehicle is into both the lane. The HERE HD maps help us draw these lanes perfectly. Every vehicle that's coming past that's noticed by the LiDAR or by the cameras, refined and placed properly in their lanes.
So all of these cars that I see around us right now, they're real cars.
They're
They're not some kind of imaginary cars. They're real cars that we've detected.
Yep.
And we know where they are in 3D space. We know how fast they're traveling. We know how fast we're traveling relative to it.
Exactly.
And we know what lanes they're all in now because we've identified everybody. We've localized everybody.
Yep. And we know the path that we're going to be taking, optional paths that we might be taking. All of this information we can present in a very refined fashion so that somebody can relax and have a serene ride down the road.
But how do we know that this isn't just a mock-up, some kind of a demo?
I think one of the best things that we can see is actually what it looks like going down the road with real information. So if we look at it with the video.
Unfortunately, we don't have a windshield in front of you, but let's put a virtual windshield up here.
Yeah, so this is the actual information driving down 101 with the vehicles passing. All of this is being computed in real time. This is not a video down below. This is
look at that. It just changed lanes. The car in front of it just changed lanes. 2 cars just come up next to us. We don't need rear view mirrors anymore. There's just no reason to ever have to look around you.
Yeah, you can just loop there is all it's doing right there.
And because our sensors are so robust and because we have so many redundant sensors, it is possible for us to detect all of these different cars around us with a great deal of confidence.
Yeah, very, very cool. And another thing you can see is the accuracy of the location. So up in the video, you see the off-ramp. You can see exactly the off-ramp happening here digitally. So we're placed very precisely inside of the lanes.
Okay. So Drive PX, doing all the sensor fusion, all the perception with deep learning, localization algorithms, path planning, essentially performing all of the computation on a supercomputer necessary for self-driving, sends the information to the Drive CX, which is now being displayed in real time so that the driver has great confidence that the car sees what they see, and the car is taking actions that are consistent with the path that they should take. Really great work. Thanks, Justin.
Thank you.
Okay. So let me put in perspective the performance that we're seeing. This is Drive PX2 compared to a Titan. Titan X is built 28 nanometers. It's used an architecture called Maxwell. It has 7 teraflops of floating point performance, has 7 deep learning tops, trillion operations per second, because it doesn't have the deep learning new instructions necessary. And it runs AlexNet, which is this famous AlexNet that won ImageNet in 2012 by Alex Kershevsky. 450 images per second. Drive PX2, because it has to support so many cameras, it has to do it in real time, it has to be able to do localization, bunch of path planning computation. So much computation needs to be done on this one processor. We felt that we needed to give it a lot more performance. The equivalent of essentially 6 Titan X's. We're going to put 6 Titan X's in Drive PX2. It's made from 16 nanometer FinFET, has 12 CPU cores. 8 of them are ARM64 A57, 4 of them based on NVIDIA custom Denver processor for very high single-threaded performance. The GPU is based on our next generation Pascal, 8 teraflops of floating point performance, 24 deep learning tops, and as a result, we can perform 2,800 images per second. We can now infer a lot of conditions around ourselves from just about any camera sensors you could imagine, and throw a lot of deep learning capability at this thing. It altogether is equivalent to about 150 MacBook Pros in your trunk. 150 MacBook Pros is about $300,000 worth of computers. We can now shrink all of that into the size of essentially a lunchbox that fits nicely in your car. So this is what it looks like. This is the Drive PX2. Thanks, Rob. Ladies and gentlemen, Rob Csongor. Thank you. This is the Drive PX2. On the front, 2 next-generation Tegra processors based on the Pascal architecture. On the back, 2 next-generation NVIDIA GPUs based on the Pascal architecture. Altogether, 4 processors, 8 teraflops of performance, 6 times the deep learning throughput of Titan X. Okay? So, one more time, 2 next-generation Tegra processors on top, 2 next-generation Pascal GPUs on the bottom. It is liquid-cooled so that we could keep this computer running comfortably, even in a car with 80 degrees C, 175 degrees Fahrenheit conditions, which are extreme by any standard. We can dissipate 250 watts in 256 cubic inches. 256 cubic inches, 8 by 8 by 4. Okay, so approximately the size of a lunchbox. It looks kind of like this. Now, if a car has liquid cooling, which most electric vehicles have, most of these self-driving cars have, you could just plumb Drive PX2 directly into it. If it does not, and you would like to deploy Drive PX2 quickly into your car, let's say next week, we have an optional heat transfer unit that is basically a fan that takes the heat away from the metal plates, the metal cooling plates and the heat pipes, and you could deploy this into your car. All you need is Ethernet, power cables, CAN bus, and you have a self-driving supercomputer that fits nicely in your trunk. Instead of what you see in today's self-driving vehicles, prototypes, filled with basically computers in the back, it's now one nice little lunchbox, and it is a supercomputer. I'm super proud to announce and pleased to announce that the first car company that's going to deploy Drive PX2 is going to be a company, Volvo, who has a heritage of extreme passion around safety. They're going to deploy several hundred cars with Drive PX to start developing their self-driving capabilities. Volvo will be our first partner. There will be many others to follow, I hope. And the last, to summarize, the NVIDIA Drive PX strategy is really not a chip strategy. It's not a processor strategy. It's an end-to-end platform strategy. It's really about, number one, helping you create the network that you can own, that you can continue to refine, because it is the driving experience of the car, creating the drive network. You can start with yours, you could start with ours, the NVIDIA DriveNet as a starting reference point. The second part of today's announcement is the NV DriveNet. The third is the Drive PX2, a supercomputer designed for artificial intelligence that we would like to use to realize the vision of self-driving cars. That end-to-end platform, that end-to-end loop is what the NVIDIA Drive PX is all about. I want to thank all of you guys for coming today. Congratulations for I welcome you to CES, and Happy New Year to everybody. Thank you.
Ladies and gentlemen, thank you for joining us today. Please proceed out the doors to your right for the reception.